Sums of cubes. In this presentation we find a formula for the summation k from 0 to n k cubed. Here n is a positive integer, so this summation from 0 to n k cubed is 0 cubed plus 1 cubed plus 2 cubed plus and so forth all the way up to n cubed. We will derive the formula using methods which can be applied to compute sums of positive integer powers of integers from 0 to n. So the positive integer power doesn't need to be 3, it can be any positive integer number p. This has important applications in integration. We have to find a formula for the summation k from 0 to n k cubed. We start by observing that summation k from 0 to n k cubed is the same as summation k from 0 to n minus k cubed. Each one of these terms, n minus k cubed, is a polynomial of degree 3 in the variable n. In the sum k from 0 to n minus k cubed, we have n plus 1 terms. The last term, however, corresponds to the value k equals n, and then n minus k is 0. Therefore, in this summation k from 0 to n minus k cubed, we have n and not n plus 1 non-zero terms. This means that the formula that we are looking for, S of n, for the summation k from 0 to n k cubed, is a polynomial in n of degree at most 4. So this follows since this formula that we are looking for, S of n, is a sum of n polynomials, each of degree 3, in the variable n. So when we add n times n cubed together, we get n to the 4th. Now cancellation might happen, so the degree may be less than 4, but it certainly is not larger than 4. This is a key observation and allows us to find a nice formula for the sum of cubes. Properties of this polynomial S of n representing the sum k from 0 to n k cubed are the following. First, if n equals 0, then in this summation k from 0 to n we have only one term, and that corresponds the value k equals 0, and therefore summation k from 0 to 0 k cubed is 0. So the polynomial at 0 is 0. The second condition is that the polynomial at the value n plus 1 is the polynomial at the value n plus n plus 1 cubed. This follows from the definition. Since s at n plus 1 is summation k from 0 to n plus 1 k cubed, we may simply first take all the terms up to k equals n, that is summation k from 0 to n k cubed, and that constitutes the polynomial S of n, and then we still have to add the last term, n plus 1 cubed. So here we have only used the definition of the sum S of n. So we find the polynomial S of n using these two conditions. It's a little bit surprising, but they do suffice. Now this polynomial is of degree at most 4. Therefore it is of the type some number a4 times n to the 4th plus some other number a3 times n cubed plus a third number a2 times n squared plus a1 times n plus a0. And these unknown coefficients ak will be determined using the conditions 1 and 2 of the polynomial S. These properties of S that follow immediately from the definition of the polynomial S as the sum k from 0 to n k cubed. The first observation is that since S at 0 is 0, a0 must be 0. Because if one plugs in place of n in this expression for S of n equals 0, we get only a0, and since s at 0 is 0, a0 must be 0. So we conclude that the polynomial that we are looking for does not have the constant term. It is of the form a4 n to the fourth plus a3 n cubed plus a2 n squared plus a1 times n. To determine the remaining coefficients ak, k from 1 to 4, we use condition 2. Condition 2 says that s at n plus 1 equals s at n plus n plus 1 cubed. In place of s of n and s of n plus 1, we plug in the expression in terms of the unknown coefficients ak. So we get that a4 n plus 1 to the fourth plus a3 n plus 1 cubed plus a2 n plus 1 squared plus a1 n plus 1 equals a4 n to the fourth plus a3 n cubed plus a2 n squared plus a1 n plus n plus 1 cubed. This is simply the condition s at n plus 1 equals s at n plus n plus 1 cubed written out in terms of ak. Next we expand and collect like terms to get a4 n to the fourth plus the sum a3 plus 4 times a4 n cubed plus a2 plus 6 times a4 plus 3 times a cubed, and that sum multiplied by n squared, plus a1 plus 4 times a4 plus 3 times a3 plus 2 times a2, and that sum multiplied by n, plus a4 plus a3 plus a2 plus a1. And this equals a4 n to the fourth plus a3 plus 1 multiplied by n cubed plus a2 plus 3 multiplied by n squared plus a1 plus 3 multiplied by n plus 1. This is simply by expanding and collecting the like terms. Next we observe that two polynomials are the same if and only if they have the same coefficients. That is, the fourth order terms must have the same coefficient, the third order terms the same coefficients, and so forth. From this we get conditions that allow us to determine the unknown coefficients ak. By expanding and collecting the like terms, we have obtained an equation regarding two polynomials. These two polynomials must be the same. And now the observation was that two polynomials are the same if and only if they have the same coefficients. Now we first look at the highest order term, that's the term n to the fourth. On the left it has coefficient a4, and on the right it has also coefficient a4. Therefore we get the equation a4 equals a4, which is rather useless because a4 is always a4. Now looking at the third order terms, on the left we have a3 plus 4 times a4, and that sum multiplied by n cubed, and on the right hand side we have a3 plus 1 multiplied by n cubed. Therefore a3 plus 4 times a4 must be a3 plus 1. This is already useful. Then next, from the second order terms we get the equation a2 plus 6 times a4 plus 3 times a3 equals a2 plus 3. And from the first order terms we get a1 plus 4 times a4 plus 3 times a3 plus 2 times a2 equals a1 plus 3. And then finally we have the constant terms on the left and on the right. We get from that a4 plus a3 plus a2 plus a1 must be 1. Here we have now 5 equations for 4 unknowns, but the fifth equation, that's the first one, a4 equals a4, is always true. Therefore we really have only 4 equations and 4 unknowns. Next we solve these unknowns out of these 4 equations. The equations for the unknown coefficients ak are a4 equals a4, a3 plus 4 times a4 equals a3 plus 1, a2 plus 6 times a4 plus 3 times a3 equals a2 plus 3, a1 plus 4 times a4 plus 3 times a3 plus 2 times a2 equals a1 plus 3, and finally a4 plus a3 plus a2 plus a1 equals 1. This looks now somewhat complicated. Of course we first make the observation that the first equation is of no use at all, because it is always true. So we are left with the four equations: a3 plus 4 times a4 equals a3 plus 1, and so forth. Now, this looks somewhat complicated and maybe difficult to solve. However, this is easy to solve, because in the first equation, a3 plus 4 times a4 equals a3 plus 1, a3 cancels out, and we are left with 4 times a4 equals 1, therefore a4 equals 1/4. So we already solved for a4. Next, we have three equations remaining and three unknowns remaining. We substitute the value 1/4 in place of a4 wherever we see it in the three remaining equations, and we get the equations a2 plus 6/4 plus 3 times a3 equals a2 plus 3, a1 plus 1 plus 3 times a3 plus 2 times a2 equals a1 plus 3, and then finally 1/4 plus a3 plus a2 plus a1 equals 1. This is simply by substituting 1/4 in place of a4 everywhere where it is seen. And again here, the first equation, a2 plus 6/4 plus 3 times a3 equals a2 plus 3, allows us to solve for a3, because a2 cancels out. We get that 3 times a3 equals 3 minus 6/4, and this means that a3 equals 1/2. So now we have values for a4 and a3. We substitute those values to the remaining two equations, and we have a1 plus 1 plus 3/2 plus 2 times a2 equals a1 plus 3. And the last equation is 1/4 plus 1/2 plus a2 plus a1 equals 1. And we have values a4 equals 1/4 and a3 equals 1/2. Now, of the first equation shown here, a1 cancels out. Therefore, we can solve for a2, and we get a2 equals 1/4. So next we substitute the value 1/4 in place of a2 in the last equation, and we get 1/4 plus 1/2 plus 1/4 plus a1 equals 1. But 1/4 plus 1/2 plus 1/4 is 1. Therefore, this means that a1 is 0. And we have our formula. We have solved a4, a3, a2, and a1, and also a0 right in the beginning. We got a4 equals 1/4, a3 1/2, a2 1/4, a1 0, and a0 0. So we conclude that summation k from 0 to n k cubed equals n to the 4th over 4 plus n cubed over 2 plus n squared over 4. This very nice formula came out of the fact that we simply use properties of the polynomial Sn. So we have derived the formula that we call formula number 3, summation k from 0 to n k cubed equals n to the 4th over 4 plus n cubed over 2 plus n squared over 4. Using the same method with no changes at all, we get the formula summation k from 0 to nk equals n squared over 2 plus n over 2. This is a well-known formula that can be derived also using easier methods. For sums of squares, we get summation k from 0 to nk squared equals n cubed over 3 plus n squared over 2 plus n over 6, and this also using these methods. Finally, in the general case, if p is a positive integer, then summation k from 0 to nk to the power p equals n to the power p plus 1 divided by p plus 1 plus lower order terms. This last formula follows using precisely the same argument. Simply the condition for the sum Sn, which in this case is that Sn plus 1 equals Sn plus n plus 1 raised to the power p. Using that condition, we get that the highest order term for this polynomial representing this sum k from 0 to n, k to the power p, is n to the power p plus 1 divided by p plus 1, and then it is followed by lower order terms. This is important for integration, because now we may observe, those who know about differentiation, that if you differentiate n to the power p plus 1 divided by p plus 1 with respect to n, you get n to the power p. And this formula 4 is in fact a derivation for a definite integral of x to the power p. Archimedes, who lived more than 2200 years ago in Syracuse, Sicily, invented integration. He computed definite integrals. He didn't know that they were called definite integrals, but he computed those anyway by methods based on explicit computations of sums of powers of integers long before differential calculus was invented. What is presented here was known already to Archimedes. Unfortunately, his inventions were forgotten and integration had to be reinvented about 1800 years later. This painting represents Archimedes. It is, of course, an imaginary image of Archimedes because it was painted about 1800 years after Archimedes. The painting hangs in Prado Museum in Madrid, painted in 1630 by artist called Ribera.